Figure 3 shows some reactions of aqueous ions. So we can see that we've got the hexa-aqua iron 3 complex in the middle, the hexa-aqua iron 2 being formed from reaction 3. Reaction 1 shows our iron 3 complex reacting with sodium carbonate, and reaction 2 shows it reacting with hydrochloric acid. And reaction 4 shows the iron 2 complex reacting with ammonia. We can see that sometimes we've got precipitates and sometimes we've got solutions. Now the thing with transition metals is if you're getting a solution, this is probably going to be an ion, and if we're getting precipitate, there's going to be no charge on the complex. So this is a little clue to help you come up with things, to help you remember your formulas. We've got to give the formula of the precipitate J. So iron 3 is more acidic than iron 2, and so can act as an acid and react with the carbonate as an acid. What that means is it's going to donate away these H's. It's going to be a H plus donor until it becomes neutral. And so it's 3 plus, so it's going to, from 3 of its waters, so 3 of the waters will remain, but 3 of them are each going to give away a hydrogen ion, a proton. And so there would be 3 of those. And that, because that is then neutral, that's our precipitate. And because it's of iron 3, it's brown. So our equation would start at the hexa-aqua complex. And we're reacting it with carbonate ions, and we know we're forming the iron 3 hydroxide precipitate, and then we'll need to look at the other products. Because it's acting as an acid, it's going to form water and carbon dioxide. I'm just going to give myself a tiny bit more space to put balancing numbers in. And now I need to balance. Now, because this iron 3 complex is 3 plus and carbonate is 2 minus, and there's no charge in any of the products, we know that these charges are going to need to balance. So we're going to need 3 carbonates for every 2 Fe3 pluses. So that will give us 6 pluses and 6 minuses. So when we come over to the other side, that kind of helps us with our balancing on the other side too. Now we have to give the formula of L. Now it's still a solution, and therefore we know that from that it's going to be charged, and therefore it's going to be a ligand substitution. And the statement in the specification is that chloride ions are larger than water and will replace them, but will only replace with 4. So all 6 waters will be removed for 4 chloride ions without a change in charge. So if the Fe was 3 plus, and each Cl is 1 minus, but we've got 4 of them, then the charge on this bracket is going to be 1 minus. Now we need to write an equation from the hexa-aqua complex, substituting the ligands. So substituting the 6 waters for 4 chlorides. You don't need to put Cl in a bracket because it's only 1 atom. And we've done a ligand substitution reaction. Then we have to suggest a reagent for reaction 3, where 3 plus is becoming 2 plus. So we need to suggest a reducing agent. Now the thing we should think about in our chemistry is that metals are reducing agents, and you need to try to make a little link to where you've probably done the reduction of vanadium complexes. Zinc is a really effective reducing agent because its electrode potential value is minus 0.76, and therefore it is most likely to be able to cause reduction and be oxidized itself. Give the formula of the precipitate M. So scroll back up. M is when the iron 2 complex reacts with ammonia. Now, ammonia is a tricky one because it could be ligand substitution, or it could be acting as a base, and therefore Fe2 plus is acting as an acid. Here, because we're making a precipitate, it's not ligand substitution. If it was ligand substitution, we'd still have a solution at the end. So ammonia is going to act as a base and accept H pluses from our complex, now because this is 2+, it's going to donate 2 H pluses. So we need to think about what that would be. We had 6 waters, but 2 of them are going to donate H pluses, so we'd have 4 waters. 2 of them have donated H pluses, and we've become this neutral complex. And because it's iron 2, it's green. The next part of the question says, transition metal complexes have different shapes and many show isomerism. Describe the different shapes of complexes and show how they lead to different types of isomerism using examples of cobalt 2 and platinum 2. So there's quite a lot going on in this question. Transition metal complexes can be linear, but that's usually for silver. They can be square planar. Now that is for things like nickel and platinum. So we're probably going to have some square planar example here. And when they're square planar, they can have cis-trans isomerism. So we're going to have a square planar complex. We're going to have to think of one and give an example of cis-trans. Then they are tetrahedral, but the tetrahedral ones don't show any isomerism. And then we have octahedral, and they can show isomerism. And cobalt would be something that would do octahedral and tetrahedral. They can show both cis-trans and they can show optical isomerism. So we need to pick our examples, allow us to answer the question with the complexes that they've given us. So transition metal complexes can be linear, e.g. that's our sort of Tollens reagent. So we're not going to have to say much more about that because it's not something of cobalt or platinum. Tetrahedral, we could do one of cobalt for that, COCl4, anything with the chloride ions. And if it was cobalt 2+, it would be COCl4 2- with 4 chloride ligands. That would be tetrahedral. That doesn't have isomerism, so that's the kind of end of that part. Square planar, I'm going to pick cis-platin, and then that, because that uses platinum like they've asked us to, so having 2 chloride ligands and 2 ammonia ligands and being neutral, that's cis. And I'm going to be able to do my cis and trans in a minute. And then octahedral, and I'm going to start off by just picking cobalt with 6 waters, but that's not going to allow me to show the isomerism, so I'm going to have to choose some other complexes. So we're going to look at the square planar complexes first, because we said that was one of the first that had isomerism. And I'm going to draw a cis and a trans version. So I'm going to draw platinum in a square planar shape, so with the wedges and the dashes showing the ligands arranged square planar around the platinum. And I'm going to put my chloride ligands together 90 degrees apart and my ammonia ligands together 90 degrees apart. And that would be the cis isomer. Whereas if I go across the molecule, across the square, that would be trans, like a transatlantic flight goes across the Atlantic. If I put the ligands, the matching ligands trans from each other, across the square from each other, I've drawn the trans isomer. Okay, so square planar complexes have cis-trans isomerism. Octahedral complexes can have cis-trans and optical isomerism. So I'm going to pick an easy complex for cis-trans to start off with. So I'm going to go for cobalt in an octahedral complex where I just have two slightly different ligands. And it really doesn't matter what I pick here. So we could have a look at one like one of those precipitates that we just had. If I put water on 4 and then put 2 hydroxides, this wouldn't have a charge, so it means I don't have to do a big bracket and a charge. These hydroxides are trans. I could then put those 2 hydroxides cis, which means put them on any 2 sticks that are not 180 degrees away from each other. So I could put one here and one here, that would be cis, and then put waters on the rest. There are a lot of options though to get 2 that are 90 degrees away from each other. So this would be a choice. Optical isomers are non-superimposable mirror image isomers. And that happens when you use a bidentate ligand. So I need to pick a complex with a bidentate ligand. It doesn't matter whether I pick the ethane 1,2-diamine or the ethane dioate ions. I can pick either. But I need to use a bidentate ligand. I can use 2 or 3 bidentate ligands and it would make optical isomers. In fact, if you use 2 bidentate and 2 monodentate, you could get cis, trans and optical all in the same complex. But I'm just going to pick a bidentate ligand. It doesn't matter whether I pick the ethane dioate or the ethane 1,2-diamine. I'm going to pick the ethane dioate. It's a bit less to draw. Although the charge is a bit trickier if you pick the ethane dioate, because the ethane dioate C2O42- has a charge. So my cobalt was 2+, and my ligands are 2-, and I've got 3 of them. And so 2+ take away 6 is 4-. I've drawn one. Now I have to draw the mirror image of it. So when I drew that first one, I started at the top and I went round this complex clockwise. So I'm just going to repeat but go anti-clockwise. So from the top to the left rather than the right, and then from the bottom, sort of the left to the bottom, and then round a little bit at the right hand side. This would be the mirror image. Put the whole thing in a square bracket and put 4-.